All right, today we are going to just take a little pause and look at the review of all the different ways that we graph linear inequalities this week. So just a quick review. This is a little snapshot of everything that you'll need, and then we'll go through a couple of examples kind of each type. So we started with graphing linear inequalities when there's only one variable. We still want to graph a boundary line, and we want to show which side of the boundary line contains the solutions. Some examples of those inequalities are listed here in red, orange, green, and blue. Now, there are also those linear inequalities in two variables. And when we see those, we have to determine, is the inequality in slope-intercept form, where the y is by itself, or is it in standard form, where the x and the y terms are both on the same side of the inequality symbol, usually on the left? Because it's going to depend, everything we do after that is going to depend on which form that inequality is written in. If it's in slope-intercept form, we are going to start by plotting the y-intercept. Remember, that has to go on the y-axis, and it's just this number at the end. Whether it's positive or negative, use that exact value. And then we plot additional points using your slope. Remember, the slope is m, or in the place of m in the inequality, so it's the number in front of x. And when we use the slope, remember that it's really two numbers. It's a rise and a run, written as a fraction. If you have a positive slope, make sure your line goes up and to the right. If you have a negative slope, make sure your line goes down and to the right. Now, for the boundary line, there are always going to be two different types of boundary lines, whether you're graphing linear inequalities in one variable, in two variables in slope-intercept form, or two variables in standard form. So you're always going to draw a solid boundary line if you have the little equal to bar underneath it, because a solid line represents that the entire line contains solutions. You're going to draw a dashed line if it's one of the inequality symbols that does not contain the equals bar underneath it. In other words, they are not equal to the value given in the inequality. So we want to draw a dashed line that represents the points directly on the line are not solutions to the linear inequality. Then, for slope-intercept form, we can just look at the inequality symbol to determine if the solutions are shaded above, or I should say if the solutions are above the boundary line, and then we would shade above the boundary line, for either of these symbols that contains a greater than symbol. Or if you have one of the inequality symbols that contains the less than symbol, so it points to the left, then all the solutions will be below the line, so we shade below the line. When it's in standard form, the way that we draw our boundary line is a little bit different, and also the way that we decide which half plane contains the solutions is a little bit different. So a quick recap from our previous lesson. If you have your standard form inequality using the numbers a, b, and c to represent those coefficients, you can find the y-intercept by dividing this constant term divided by the number in front of the x. So we call it c divided by a will give you the value of the x-intercept. The y-intercept is when you take the constant term divided by the number in front of the y variable. C divided by b will give you the value of the y-intercept. And that's going to help you find the positioning of the boundary line. We draw the boundary line the same way. Solid line if it's one of the or equal to symbols. Dashed line if it's not equal to. But instead of just shading above or below using the symbol, we have to test a point for standard form inequalities. So 0, 0 is one of our, well, it probably is the best point to use as long as it's not immediately on the boundary line. If it is, pick something else like 1, 1, or even 1, 0 or 0, 1, anything that's not on the boundary, something that's clearly on one side of the boundary, because we shade the side that contains the solutions. So if 0, 0 is a solution to the inequality, we shade that side of the boundary line. If it's not a solution to the inequality, we shade the opposite side of the boundary line. So let's look at some examples and practice. All right, example number 1 says to graph x is greater than or equal to -2. Now I remember when we only have one inequality, I'm either going to be graphing a vertical line or a horizontal line. Excuse me, only one variable in the inequality gives you a vertical or horizontal line. So the variable tells us that we want to go through the x-axis, in this case at -2, at an exact 90-degree angle. So we want to go through the x-axis perpendicularly at a 90-degree angle. So that's going to go kind of like right through here like this. Now notice I didn't draw the whole line because I have to watch out for, sometimes I graph solid boundary lines and sometimes I graph dashed boundary lines. But you remember from our review, if it has the equals bar underneath it, we draw a solid boundary line. So I'm going to go ahead and draw that solid line. Try to keep it right on that grid line where x equals 2 all the way along it. And I extend my boundary line all the way up and down. And now I'm just realizing that I put it at 2 and not -2. So I better move that over. And let's just erase that. All right, teachers make mistakes too. Thank goodness I caught it before sending this video your way. All right, so solid line going through the x-axis at -2, right there. And we want to shade where all the solutions are. So where are all the ordered pairs that have an x coordinate that's bigger than -2? And that's going to be to the right side, because x coordinates or x values along the x-axis, these are your numbers that are bigger than -2. So anything else on that side is going to be where we have our solutions. So I'm just going to shade everything to the right. Everything over here. All the way up to the boundary line. Don't stop at the y-axis. The y-axis is not a boundary. Only the line that we drew is the boundary. All right, with number 2, this time we have y is less than 3. So because y is the variable, I want to go through the y-axis at +3. Let's see if I can put it at the right spot this time. So the y-axis has a value of 3 right there. And if I'm going to draw a line that goes through the y-axis at 3, through it at a 90-degree angle, I would need to draw a line that goes across my graph. But before I draw that, I'm reminded that the symbol that's less than but not equal to is one of my symbols for a dashed boundary line. So I'm going to draw my dashed boundary line. Arrows on both ends, extend my line all the way across the graph from left to right. Now I need to think about where are those numbers, where are those y values, so think y-axis, that are less than 3. Well, right on the line is where y is equal to 3. So everything below it is where I'm going to have these numbers that are less than 3. So I want to shade everything below the boundary line in this case, underneath it. Y is less than 3. All of the ordered pairs in the yellow shaded area have y coordinates that are less than 3. That's where all the solutions are. All right, next, number 3, we're graphing y is greater than 2/3 x minus 4. I recognize that y is by itself, so I have to follow my rules for slope-intercept form. So when I look at my inequality, I can see that my slope is positive 2/3. My y-intercept is -4. And then I also see that my inequality symbol is greater than. Because it's a greater than symbol, that tells me to draw a dashed line. Remember, greater than but not equal to. Not equal to is the dashed line. And I want to shade, let's see, greater than, bigger numbers, I shade above the boundary line. So dashed line, shade above, and I can use my slope and y-intercept to put my line in place. So I want to start at a y-intercept of -4. Then I'm going to use my slope of 2/3. Remember, positive slopes, I want to go up and to the right. So I'm going to rise 2, run 3, up 2, right 3. Or I can go backwards, down 2 and back 3. And when I draw my line, remember that we need to use a dashed line. So a dashed line across the graph all the way across the grid. And I want to shade above the line, which the upper side looks like actually the upper left-hand side in this case. Shade everything up here all the way to the boundary line. Try not to leave any areas of the graph unshaded. Okay. All right, and that's how we graph all the solutions to that inequality. Everything in the shaded area is a solution to that inequality. Number 4. We see again that the y is by itself, so we're going to use our slope-intercept form, or slope-intercept method of graphing. I see that my slope is -2, but I'm going to go ahead and write that as a fraction right now, so I have my rise and my run. My y-intercept is 3, that's just the number added at the end. And then my inequality symbol tells me 2 things. The first item is that it's greater than, so I'm going to shade above the line, because remember, greater than, think higher numbers, bigger numbers, shade above. But then I also have the or equal to, and that's just going to tell me to draw a solid line to indicate everything on the line is also a solution. All right, so let's get our line in place. I start with a y-intercept of 3, remembering that I'm on the y-axis, not the x-axis. And then from that point, I am going to make sure that I go down for a negative slope, down and to the right, down 2, right 1. Looks like I can do this quite a few times until I run out of space. I could even go backwards one time. And let's see, I've got my y-intercept, I've got my slope. Now I need to draw a solid line through those points. Try to extend that all the way across the graph in a straight line. And then I want to shade above the line. So everything above the line is a solution. The upper side actually looks like the right-hand side, but it's the upper right side on this example. Again, kind of shading all the way up to the boundary line. Trying not to skip any parts or areas as best we can. All right, that is all of the solutions to y is greater than or equal to -2 times x plus 3. For number 5, we see now that y is not by itself. This is actually standard form where x and y are on the same side. And for standard form, to figure out where our line is located, we have to identify the a, b, and c. So a is -1, b is +2, c is +6. My x-intercept is when I take the constant value and divide by the number in front of the x. My y-intercept is when I take the constant term 6 and divide by the number in front of y. So my x-intercept is -6, my y-intercept is +3. On my x-axis, I plot my intercept at -6. On the y-axis, I plot my intercept at +3. I can draw my line through those 2 points, but before I do, I have to check to see what type of line I should draw. Because of the less than or equal to, I'm going to draw a solid boundary line. So let's see if I can draw this straight the first time. There we go, solid line all the way across, going through both intercepts. Splits our graph into 2 sides. Now I can't just use my inequality to say, oh, it's a less than sign, shade below. It might be, but sometimes we shade above when we have standard form inequalities with less than signs. So instead we have to test a point. I can see that the origin, 0, 0, is clearly not on the boundary line. So that would be an okay point to use. And I remember what happens when I plug 0 in for x and 0 for y in my inequality. Okay, I just took my inequality and replaced x and y with zeros. And this whole thing, -0 plus 2 times 0, is just going to equal 0. So a quick check to see if 0, 0 is a solution. Let's see, is 0 less than or equal to 6? Well, I know they're not equal, but is 0 less than 6? Yes, it is. So that ordered pair is a solution. Since 0, 0, or the origin is a solution, that means so is everything else on that side of the boundary line. So we are going to go ahead and shade below the line because that's where we have the solutions. We tested one point to see if it was a solution, and it was. All right, we have just one more example in our review today. 8x plus 12y is greater than negative 24. So we can see our A is 8, B is 12, C is negative 24. We definitely can tell it's in standard form because x and y are together on the left-hand side of the inequality symbol. So we're going to follow our process for finding the intercepts. I'm going to take the constant term divided by the number in front of x. For the y-intercept, I'm going to take my constant term and divide by the number in front of y. Let's see, negative 24 divided by 8 is negative 3. My x-intercept is at negative 3. For my y-intercept, negative 24 divided by 12 is negative 2. So on my y-axis, I plot my point at negative 2. I'm going to go ahead and draw my line. See if I can do this. Before I draw, what type of line do I need? Oh, it's greater than but not equal to. So I actually want to draw a dashed line. Good thing I remembered to check that. A dashed line that goes through the intercepts all the way across the graph. Try to keep it as straight as possible. And then I have to determine where to shade. All right, well, the greater than symbol, oh, that's right, it's standard form. I can't just look at the greater than sign and say shade above, because sometimes we shade below for greater than signs in standard form. That little trick only works for slope-intercept form. So let's see, let's test a point. I can see that the origin 0, 0 is not on the boundary line. It is clearly above it. So let's test that point. When I plug my zeros in for x and y, test 0, 0, I do 8 times 0 plus 12 times 0 is supposedly greater than negative 24. Well, I know that 8 times 0 plus 12 times 0 is 0. So I have to check to see if this is true. Is 0 greater than negative 24? Well, yeah, 0 is bigger than any negative number. So that would be true. And since the origin is a solution, 0, 0, right there, that means everything else on that side of the boundary is also a solution. So I'm going to go ahead and shade the side that contains the origin because the origin is a solution. Trying to fill this in as much as possible to show all these solutions over here. All right, so that is our review for today. Reviewing the linear inequalities with one variable, slope-intercept form, and standard form.